everyone, this is Sravana working as Assistant Professor in EC Department. Today's topic is we'll discuss about the register organization of 8086. So, register organization, as we have discussed, what is 8086 and how many pen IC it is and internal architecture. Those are nothing but the features of 8086 have been discussed already. Today, today we are going for a register organization. So, what is a register organization? So, we need to process some operations in 8086. Right? How you will process all the instructions in 8086 is the data will be stored in the memory and will take the data, will fetch the data and will decode it and execute it. So that is what we know, that is instruction cycle. Right? So in order to execute any program, we need a storage element which is present in an 8086 apart from the memory. So apart from memory, we have a register which is nothing but it's a temporary storage. Temporary storage. So today we'll discuss about the register, how many temporary storage elements are present in an 8086 and what is a register, what is the use of a register, and how many types of registers we have in 8086. Right? So here, first, what is a register? Register is a temporary storage area built into a CPU. Right? So it's in temporary storage. So when it's like, you can say it's a random access memory. It's a programmable. So a register is always a temporary storage where you can store the data and you can erase it, or else you can rewrite the data into the register. The new data, whatever you are going to access, the new data can be always accessed, always placed on the register. That is nothing but overwriting a memory. So here a register can hold an instruction, it can hold the address, it can hold the data, and it also operates the instructions which are specified in some register. So that are the main use of using a register in an 8086. So you can say you can hold an instruction, you can store an address, and you can take any data in order to operate it, and and you can call those instructions, the specified instructions which are stored in the register in order to operate. So, and here you can say then what is the difference between a memory element as well as a register? You have a memory, you have a register also. Both are present in an 8086. So what is the use of register? You can say register memory is the smallest and fastest memory in a computer. So in order to make operation as faster, you can go for register for the storage. It may be an instruction, it may be holding some data, or it may be storing some address where you will have some set of instructions. So it only temporarily holds the data and it can be accessed by taking the memory address of the CPU, and these are passed through the registers. So in order to access the operations in a CPU, the register are directly sent. This is a register, suppose. In register which we are storing the data, so directly the registers are sent to the central processing unit in order to execute. So suppose if you have a memory is nothing but it's a large amount of storage element. So that memory takes more time in order to take out the data and send to a central processing unit. So the easy way is you can store the data into different registers where it can be accessed very easily in the less number of time. So that is what the use of the register. So here, how the register can be defined. The antinomy of the register, if you go for, this is a antinomy of the register. Here, you can say the length of the register can be 0 to 7 bits. Those are called as lower byte register, and 8 to 15 register are called as higher byte register. And so this lower byte and higher byte combined, you can say the bits will be from 0 to 16. So 0 to 16 means you can say it's a 16 bit where it is called as a word. So the registers which stores a 16 bit are called as the 16 bit, that is, it stores the word. Okay, so and apart from this word register, those are called as word register. Word register is nothing but what? We are storing the data of how many bits? 16 bits. So that 16 bit can be again divided into two groups. One is from a bit 0 to 7. 0 to 7 is low byte register, and 8 to 15, the another set of the data bits which start from 8 to 15 can be said as higher byte register. So this is what how a register can be defined. So apart from this word register, you can also extend the register that can be of 16 to 31 bits. So if a register is extended greater than 16 bit, it can extend up to 31. Right. So that 31 bits can be said as extended register. Right. So here, the register, you can, now you're saying a register is a storage element, right? This storage element stores how many bits? It can store a 16 bits, which is of a lower byte register, you can say from 0 to 7, and higher byte register from 8 to 15. And the extended can be taken from greater than 16, that bits can be extended up to 31. That register is called as extended register. So this two registers, in this two registers, our 8086 can use only word register, because the 8086 can only access a 16 bit, because it has 16 data links. So all the registers which you are, which I'm saying, we have a register organization. We have so many registers. How many bits those can access are 16 bit. So now we are seeing the register. What is a register made of? Register is made up of a flip flop, where flip flop is nothing but a storage element. So, in order to compute a hardware, all the register circuits are composed of flip flops, and the characteristics are similar to the memory. So, what does a memory does? Memory does the read and write operations of the bits at a time. Here, you can here we can see we have a different set of registers. This is a general purpose register, you can say. This is nothing but index register, and these are status and control registers, and these are the segment registers. So these each element of this are made up of flip-flop. So all the registers which are used as a temporary storage element will be designed by using a flip-flop. So flip-flop generally act as a memory element, and it goes for read and write operation of the bits. So as we have discussed the previous antonymy of register, in that the word register and extended register is present. So word register is used for 8086. So all the registers which we have here, all registers are of 16 bit, right? So here, let us now come into the individual registers. So here first we'll look after the general purpose register. So the general purpose register, the name itself says general purpose. General is nothing but the basic operations which I am manipulating or executing in my microprocessor. So what are the main operations? A general simple operations always you go for is nothing but addition, subtraction, multiplication, and division. So these are the basic operations. Not only the basic operation, these operations used to write programs in order to execute any devices, right? In order to execute any operations or any application, if you want to design, you can use these basic operations: addition, subtraction, multiplication, and division. So that is what you are writing a logic in different ways by using a for loop and an embedded C programming like that. So these are basic operation. The basic operations like addition, subtraction, multiplication, and division are done by using a general purpose register. So here these general purpose registers are divided into four. First one is AX register, AX. Next one is BX register. Next one CX and DX register. Each of how many bit is 16 bit. All are 16 bit. So this 16 bit can be again divided into a lower bit, that is nothing but 8 bit, and higher 8 bit. So you can use this register separately, like a lower 8 bit and higher 8 bit. Always make sure whenever you are giving a data into this register, always the data will be stored first in the lower bit. Next, it may be 8 bit or any bit, how much you are giving, but it will be always less than 8. So less than 8 bits will be always first stored in the lower, right? And next bits, the next bit will be occupied by the higher bit. So the lower bit which is storing the data, lower 8 bit which is stored in always an AL register. So you can say AX is a combination of AL as well as AH, where AL stores the lower 8 bit data and AH stores the higher 8 bit data. And it is the name A is given as an accumulator register. We'll see in detail next. And next one, so this is an 8 bit spacing which stores an 8 bit. This is another 8 bit. Similarly, the BX register. BX register, the B indicates like base register. So it used to store the offset address. Offset address. So again, it is also divided into a lower 8 bit that is called as a BL register and higher 8 bit that is called as BH register. And next one. Cx is nothing but the C indicates it's a counter. Cx indicates a counter register. So what is a counter? So again the Cx is also divided into lower 8-bit and higher 8-bit. That is indicated by CL register, and higher 8-bit is indicated by CH register. So C indicates it's a counter. So if you're going for a string kind of operation, we need to give how many bits you are assigning. Suppose you are giving a input values, string input values of five numbers. So what will be the count is 5. So initially we are assigning a count whenever you're going for loop kind of operations, string kind of operations. We need to assign the count, how many how many times the loop should be repeating, or how many memory locations we need to assign in order to give the string of data. So all these are made by using a counter register. So counter register need to store the count. In order to initialize the count, we need a counter register. Next is DX register. So DX register is nothing but D indicates it's a data register. So data register, it stores the data. That is nothing but similarly like AH, BX and CX. Similarly, the data register, which is of 16-bit, is also divided into lower 8-bit, that is indicated by DL. L indicates lower, H indicates higher. So another higher 8-bit data is stored here. So this is what a general purpose registers are. So how many registers we have? General purpose register, 4 register, where each is used for general operations like addition, subtraction, multiplication and division. So AX is nothing but the accumulator register, BX is nothing but the base register, CX is nothing but the counter register, DX is nothing but the data register. Okay. Here now we'll see the next set of register. So next set of register are index register. What is an index register? So here we have 4 registers where SI and DI are the index register, and BP and SP are the pointer register. So combination of pointer and index registers are shown here. So BP is nothing but the base pointer, SP is nothing but the stack pointer, SI is nothing but source index, and DI is nothing but the destination index. So you can write here, this is the base pointer. This base pointer. So the name you can say base pointer. Pointer is nothing but what? Pointing out to one particular memory location. So always if you go for the segments, we'll see the what is meant by segment, or else the memory. In memory, some address, the data will be stored, like some instructions are stored. This base pointer is used to store the offset value of the segments. So that is what a base pointer is. Stack pointer. Stack pointer is nothing but, stack is nothing but a part of the memory. Means you have a memory. That is also a memory. You have a RAM. In that RAM you have a stack. Stack is a part of memory which is used to send the data and take the data. In order to send the data, we need an instruction, push instruction, and in order to take the data, we'll use pop instruction. So, stack pointer, whenever you are going to operate with a stack kind of operation, we need to store the base address. which it need to point out. Suppose this is a stack. In the stack, in which memory location I'm working, I need to know. So that memory location can be indicated by stack pointer, right? So always in a stack, suppose this is a stack, this stack has memory locations, right? It may start from 2000, 2001, 2002, 2003, and 4. So, if my pointer, if my stack, my processor is working in 2002 memory location, how would I know? How we can know? Processor knows, but how we can know? That can be stored in the stack pointer. So, stack pointer point outs in which memory location, in which stack memory location now it is executing. Now my processor is executing 2002 means my stack pointer should store 2002 address. So it is pointing out to the memory location which I am working. And next, source index and destination. These both are two index registers, each of 16-bit. Always make sure any register which you have here, it may be a general purpose or it may be a segment register, index register, all are of 16-bit only. So only it can store 16-bit content, not more than that. Now, see here, source index and destination index. So source index. If I need to give some string of data, I need to assign that memory location to source index. Source is nothing but if you want to give a data into a memory location, you can assign that memory location into the source index. Suppose I'm in my memory location, I need to load the program in 3000 memory location. In 3000 memory location. So this 3000, that is nothing but string of data like 1, 2, 1, 2, 3, 4 is a data which I need to give in the memory location 3000, right? So 3000 is nothing but what? A memory location where I need to give the input data. So this 3000 can be assigned to my source index, where by assigning some count, I can give my string operations. So I am giving an input value to some memory location of the count of 4. So I need to assign source index. Means to give a input data, I need a source index. So you can write move si comma 3000. In 3000 is a memory location which is assigned to SI. So here you can see you have how many count here? 4 count. So before this you need to assign the count also. Move CX comma 04. So my source index which I am giving the input data, which is an address of 3000, will occupy 4 memory location from 3000 to 3001, 3002, 3003. 4 memory location it is occupying in order to give my data of count 4. So to give the data, we need a source index. That is a basic thing. Next, destination, DI. DI is nothing but what? Destination. Destination index means you are seeing the output in the location where I need to see. As I said, I have given my SI input in 3000. I need to see my data in some other memory location. So in some other memory location like 5000. So this 5000 address is called the destination now. So you can call it as destination location. So this location can be given by the DI register. So in order to see my output, I need to assign the memory location to destination index. Like you can say Now I need to see my output, this output, same output 1, 2, 3, 4, and 5,000. So destination address I need to write as move di comma 5,000. Right. So in order to see my output values, I need a destination index. So these are the index and pointer register. Pointer registers, you have two pointers. The pointer indicates we need to point the offset address of the base register, or else the offset address of the stack segment. This is of data segment. So in order to point out some memory location which you are working, you go for a stack pointer and base pointer. If you are sending the output, and if you are getting the output in some memory location, we can assign as to send the input into the some memory location, we'll write as SI, and that is nothing but source index. In order to get the data in some memory location, you will write it as DBI, destination. So this we have completed. Next register are status and control. Right. So status and control are includes both are 16-bit, and first you have a 16-bit flag register. This is a flags. So actually what is the use of a flag? Flag is nothing but in order to show you the output status of our CPU. So if a CPU are executing a more number of instructions and it is sending the output, whenever it is working, you need some interrupts. If you are having some interrupts, or if you are having a carry, or if the resultant is 0, or if you are having an auxiliary carry. So all these, the output status of the CPU will be shown by the flag register. And also you can say flag register is of 16-bit. And next, instruction pointer. As all we have discussed the two base pointer and stack pointer, instruction pointer also works the same. Instruction pointer shows you the address in which you are working. Instruction pointer. So it points the memory location in which our processor is working. Next, we have segments now. So segments, what are segments? So you can say how much memory we have discussed in the features in previous slides. 2000. How many address lines you have? 20 address lines. So 2 power n is nothing but address lines will give you the memory location, that is approximately 1 MB. Right. So how much memory does we have in 8086 is 1 MB memory. So this 1 MB memory is divided into different logical segments. Different logical segments. Right. These segments each of 64 kilobytes. Each of 64 kilobytes. Those segments are the code segment. CS means code segment. Next, SS means stack segment. DS means data segment. ES is nothing but extra segment. So these are the different segment. Each of how many bit is 64 kilobytes. So our 1 MB, what is the need of dividing this? We'll see. We'll have the segmentation also. The topic we have segmentation. Why we are dividing our memory into this code segment, stack segment, data segment, and extra segment. So you can say in order to process a faster, you can use these segments. Suppose I have written a code of a stepper motor which I have connected. I need to execute a stepper motor program by my microprocessor. what I need to do? I need to write a program in an assembly level language, right? So this assembly level language, this is nothing but the code. That code I need to store in some memory location. So directly I'm storing the code in a code segment, right? And the information or the input data which are related to that, I'm giving in the data segment, right? So means what we are doing, according to the input data or according to the data which you are sending to the microprocessor to execute, we are storing that content into some considered memory location to make our operations faster. So if I go for a if I go for a stepper motor code, so as I know, it is directly stored in the code segment, so there is no need of searching for my processor. So searching the code where I've in which memory location I've kept will be taking more time in order to execute and in order to get the output. So we are storing the content into some particular memory location, and you're giving that name as the code. So what all the code what all the application oriented the code which you have written in an assembly language directly will be stored there. So so in that particular memory location, you can take it and access it. So in order to find out easy way in order to execute, we'll go for segment register. So in detail, we'll see in the segmentation topic, right? So now let us go for general purpose register. In what are the general purpose registers? See here, accumulator. AX is nothing but the accumulator. BX is nothing but the base register. CX is nothing but the counter register. And DX is nothing but the data register. So here you can see AX accumulator needs to take the output, and the base register need to store the offset address, and CX is used as a counter register, and DX is used to point the data into the IO operations. So here you can see all are storage, temporary storage. All these registers are of temporary storage, where each register is of 16-bit wide, and it can be accessed either 16-bit or 8-bit. So that is nothing but lower or higher. So AX is a combination of what? AH as well as AL. So what is an AX? AX is an accumulator register. It is preferred to use the arithmetic and logical data transfer instruction because it generates the shortest machine code. So here, whenever you are writing a program in your if you're writing a program for any application, what the main thing is, you need to write a program, the set of instructions which occupies very less memory, right? So if it is occupying less memory, it can be executing more faster, and result will be also in fast. So what we are doing is we are choosing the AX register for arithmetic and logical and data transfer instructions, where this occupies very less number of machine opcodes. Opcodes are less. And next, and it can be used in the multiplication and division operations, and it also used in the IO operations. IO operations are nothing but whenever you're going for external devices which you're connecting, in order to make those external devices the port address if you need to give. So all this kind of application, you can use this AX register. So AX register can be used for arithmetic logical operations and IO operations because it gives a very less number of opcodes. Next, BX register. BX register is a base register. It serves the address register. Next, CX is nothing but a counter register. It is used as loop loop counter. Means if you need to go for iterations, in that cases you need to give a count. So that count can be given for CX register. Next, it is also used for shifting and rotation operation. If I need to shift my content to right or left for 1 bit or 2 bit or 3 bit or 8 bit, I need to shift. So directly by using the shifting operation SHR, the AX comma C, AX comma you can directly give the value with how many bits I need to rotate to the counter register. And you can rotate the operations also. Rotate the operation right to left. Right. So this are the operations, some operations which can be used. Means iteration, if you are going for, or if you are going for string kind of operation, you will use a counter. Next one is data register. DX is nothing but the data register. It is used for multiplication and division, and it is also used for IO operation. So here, whenever you are going for multiplication and division, the if you're multiplying 2 16-bit, the output bit will be more than the 32-bit. So all the registers can store only 16-bit. So what about the remaining 16-bit? The remaining 16-bit can be stored in the DX register. Right. So that is what the use of the data register, and also it can be used for some operation, input output operations. Next, so the pointers and index registers. This is a pointer register where you in order to point out the stack kind of operations, we use a stack pointer. Base pointer is nothing but whatever the data segment or extra segment we need to serve the offset address, it can be used as a base pointer. And source index and destination index can be given as input and output, and instruction pointer. So what is an instruction pointer? It always it stores the address of next instruction that is to be executed. So, and apart from this, it also acts as an offset register for CX register. Next one is base pointer. Base pointer stores the base address of the memory, and it acts as an offset for the stack segment. So those are next one is stack pointer. Stack pointer points the current top value of the stack. Like the base pointer is also like a base pointer, how it is storing the offset. And it in the stack pointer also indexes the extra segment address. Usually whenever you're going for a particular copy, the block of memory from another new location, like sending your data from one memory location to another memory location, like from 2002 if you're sending the data in 3000. And next, source index stores the offset address of the source segment, and destination index stores the offset of the destination. So these are the index and pointer, where you can you can say an example here. All are 16-bit, which can access a lower and higher byte. And here these memory locations, here you have an example where SI is assigned with some memory location, which I'm giving a two addresses of 2000, where in 2000 I have given some values. That values are moved into AH. So here, move a byte stored in the memory location whose address is contained in the register SI to the register AH. So bracket indicates that in that memory location, the square brackets, if you can see here, this square brackets indicates that in this memory location, whatever the content, that content is moved to the AH register. So IP is not under the control of a programmer. IP, as we have discussed, is an instruction pointer. This will not be controlled by the programmer. And flag, next we'll go for the flag register. So flag register, as we have discussed, here the flag register shows the status of the arithmetic and arithmetic operation. It stores the status of the arithmetic operation. There are two types of flags. If you can see, you have a status flags and the control flags. What are the status flags? Is status flags will be automatically set and reset according to the operations which are done in the CPU, controlling unit. And control flags are nothing but these can be enabled and disabled according to the processor use. Right. So we have two types of flags: status according to the CPU operation, and control flags cannot be disabled by the operation CPU operations. So here you can see this is a flag register which is of how many bit? Is 16 bit. So you can write down here. This is a flag register D0, D1, D2, D3, D4, D5, D6, D7, D8, D9, D11, D12, D13, D14, and D15. So, how many bit data are a flag register? Is a 16-bit data. Here you can see first D0, CF indicates it's a carry flag, and D1 is the cross indicates that it's an undefined. Undefined is nothing but we are not using that bit memory location. Bit memory location. Right. And next one is PF is nothing but the parity flag, and here D3 is another another bit where you're not defining anything for it, and D4 is nothing but auxiliary flag, and D5 is nothing but don't care condition, means you're not defined that, and D6 is nothing but zero flag, and D7 is a sine flag, and D8 is a trap flag, and D9 is an interrupt flag, and D10 is a direction flag, D11 is a overflow flag, and these 4 bits are undefined. Undefined flags. Undefined flags. So this is an actual the register where each bit. So why these bits, some bits are not defined are, if according to the user, he can use these undefined memory location to some other. So first, here you can see OF is nothing but an overflow flag, DF is nothing but the direction flag, IF is nothing but the interrupt flag, TF is nothing but the trap flag, and SF is sign, zero flag, auxiliary carry, parity, and a carry flag. So here you can see all the status flags are indicated in the orange. So overflow flag is automatically generated by the operations whatever you have done in the at the CPU, and sine flag is also set and reset according to the operations which are done, and zero flag if the resultant is zero, and auxiliary carry if you are having from fourth nibble to next nibble, if you are having a carry, auxiliary carry will be set. Parity is nothing but if you have an even number of parity or odd number of parity. Next, you are going for carry bit. At the end, if you have a carry bit, then the carry flag will be set. So here, these are called 6 flags are called as status flags. It will be automatically set and reset according to the CPU operation. Next, these direction flag, interrupt, and trap flag are only accessible by the by the application. So the people which you are writing a program. It can be accessed by is. That is nothing but the 3 flags. Whenever you are writing a program, you can set the direction of SI and DI. Either I need to increment or either I need to decrement. Or if if you're connecting an external interrupt device, the interrupt will be enabled. And if you go for a single step execution, the trap flag will be equal to 1. Single step execution is nothing but step by step. So if I have given a set of instructions, one after the other, the instruction will be executed. If there is an error, then you can find out very easily whenever you're going for single step execution. And whenever you're going for the if you're not going for single step execution, all the instructions, whatever you have, about 1 to 10 instruction will be executed, and directly you will get the output. So again, see trap flag. Trap flag is set when you're using a single step execution. That is nothing but whenever you're debugging a single instructions, and this flag will be 0 and the feature will be off, and this flag will be set by INT instruction. Next, status flags. In that, we are going for carry flag. The carry flag is of unsigned arithmetic operation. It is large in order to fit the memory location. So if the output is having more than the prescribed 16-bit, you will get a extra bit. Whatever you are having, that bit is called as a carry. So the carry bit will set whenever it is equal to 1. If you are not getting any carry at the end, more than the 16-bit, if you are not getting, then it will be equal to 0. That is no carry. And next, overflow flag. Overflow flag is set when the signed operations are too large in order to fit the destination register. So in that cases, it will be equal to 1. Otherwise, it will be equal to 0. And next one, Sine flag. Sine flag is used if MSB bit, if it is 1, it means you are going for negative, and if it is 0, you are going for positive. And next one is a 0 flag, and this flag will set whenever the output is, the result is 0. 0 means the result, if the result is 0, then it will be equal to 1, and if it is result is not 0, then it will be equal to 0. Next, auxiliary carry. Auxiliary carry will be shown whenever you are going for lower 4 nibbles to higher 4th nibble. Then if you are having a carry from lower nibble to higher nibble, then the carry value will be 1, or else it will be equal to 0. Next, the parity flag. Always you make sure the parity is always given in order to, it is used for error detecting and correcting. So if the value, if even number of values if you have, it will be equal to 1. And if it is, you are having odd number of values, then it is odd number of ones, it will be equal to 0.
Like, share and subscribe. Hit the bell icon for more updates.